All right, everyone, let's get started. Sorry, I'm a couple minutes late. So I'm going to start out by just reviewing quickly everything we covered on Tuesday. Are there any questions about the syllabus or the way the class is organized? Yes.
Your total for the percentages for the A and above was all the way to 115%, but your total was only 100%.
Ah, yes, yeah. So I must have copied the grading scale from 611. At 611, we had you could opt out of the exam or the project at the end. So I'll fix that. Thank you. Yeah, this one just adds up to 100 scores. So we will be assigning the first lab next week. So make sure you choose a lab partner and email that to me. If you really want to work alone, you can, but I estimate we only have about 5 slots for single member teams based on the number of workstations and boards we're going to have. So those will, be first come, first serve. But if you want to work in a team, which I recommend, then just make sure you send me your team members by Tuesday. Okay? All right. So last time I defined what a embedded and cyber physical system is to kind of give you an idea of what sort of systems we're targeting in this class. And we talked about this notion of a trade-off between performance and cost, and performance and size or footprint or cost, or however you want to think of that. And so the idea is that there's different processors with different capabilities and different trade-offs. So we went from the 8-bit Arduino, which is pretty much the lowest power processor you can get, I think, right, Alex? I don't think there's really anything that's less power and less performance than the Atmel 328P. It's kind of the one side of this spectrum. Right, it's literally the same processor that powers these greeting cards in the drugstore. And then, of course, on the other side, you have, really high-end processors. The Neos processor that you use in 313 is, somewhere around here, right? And then this ESP32 that we've chosen for this semester is, farther to the right. So this is more powerful than in terms of computational capability than the Neos 2 that we use in 313. Of course, the chip, though, I mentioned that the chip that we're using has 48 pins. The FPGAs used in 313 have 780 pins, so a much bigger chip, although the actual processor that we use in that class uses like 3% of the FPGA. So the FPGA is very capable, but the processor that we use was kind of a lightweight. Okay, all right, so so my point of this slide, and I used to talk a lot more about this in the past, but the point here is that you have to match the processor to what you want to do with it. So embedded systems are when you're designing a bespoke system for a specific application. You're designing hardware for a specific application. You're designing, hardware to control an elevator or a gun turret or, a drone. You have to choose the hardware according to what you need it to do. And there's a lot of different types of processors out there. So we've just chosen one for you. In the future, where I see this course going in the future is that you guys will pick the processor. We won't have to pick it for you. And you guys will pick the application too, the project. We're still kind of in the early phases where we're providing the processor and the projects for you, right? Okay, so then I talked about programmed I/O. Is there any questions about this? Programmed I/O is essentially just where you associate each peripheral with a magic range of memory addresses that you load from or store to. You can't choose this on a fixed architecture. You can choose this on an FPGA like in 313, but you can't choose it if you buy a chip off the shelf. And when I say peripheral, back in my day, your CPU was on a chip, and all your peripherals were on other chips, and they were connected by wires on a circuit board. These days, when I say peripheral, I'm talking about peripherals that are on chip. So there's one chip that has a CPU, and on the ESP32, I would estimate that the CPU is maybe 20% of the chip real estate, and the other 80% are all these peripherals and other stuff they have on there. It's the same thing with your phones. In fact, if you guys probably remember in 611, I used to have a slide still have a slide when I introduced that course that shows the Apple chips, the Apple chips where Apple doesn't release die images like Intel does, unfortunately. But guys, whenever a new iPhone comes out, they buy it, they tear it apart, they take the die out of the chip carrier, and then they take a micrograph of it. And then they try to estimate where the CPUs are and where the GPUs are and where the AI processors are and where the modems are. And they don't always get it right. But I have pictures of that in my 611 slides. And in the Apple chips, the CPUs are really tiny, right? Because they pack so many things on those system on chips. So when I say peripherals and when I talk about CPU talking to peripherals, I'm talking about the CPU communicating with the peripherals over some kind of an on-chip interconnect, a network on-chip. And we don't know what that looks like on the ESP32. I have no idea what that looks like. But in 313, we talk about a little bit, it's the Avalon bus, right, in 313. And even then, you don't really get to see it because all that Avalon architecture gets generated as part of the platform designer. When you guys design everything in the platform designer and you hit the button and it generates that big blob of system Verilog code, all the bus arbiters and all the infrastructure is included in there, right? Okay, so then we talked about bit twiddling. I spent most of the lecture on bit twiddling. Was this clear? Any questions about this? So the idea is that we need to be able to treat these words as, when I say word, I mean a value that we load from a peripheral or store to a peripheral. They have to be, generally they're treated like structures. So you have one word that's 32 bits, but there's multiple fields in there. There's multiple parts of it, right? As opposed to dedicating a whole word to a specific purpose, right? So you're going to have to do this thing where you extract bits and you insert bits. And the problem is, and I alluded to this last time, there's a lot of potential for bugs when you're doing this. This is the issue, and I say this from experience. You might have the address wrong that you access, or you may do this bit twiddling wrong. And it's very hard to track those kind of bugs down. That's an annoyance. So just be careful. And bugs can manifest because of order of operations, because, and maybe you might be a better programmer. In fact, the chances are you guys are better programmers than I am. But I tend to do a lot of this stuff like this, where I write this complex inlined expression where I shift something and negate it and bit mask it all in one line of code. And so when you do this, and you tend to do this a lot with embedded programming because you're doing so much of this bit manipulation, but when you do this, you leave a lot of possibilities in this line of code of there being a bug, right? And you can't really, it's hard to do, and of course we have to do print debugging, as I mentioned too. We don't have a debugger yet on this platform. So it's not like you can go in GDB and figure out what's going on here. You have to basically use print debugging, and then what do you print? You print the whole expression, or you try to break out pieces of it. It's difficult. I just want to warn you that it can be annoying and frustrating to do this. Okay, so we talked about isolating bits and setting bits, and there's different ways to do it, but in general, it depends on shifting and masking, right? Shifting and bitwise operations. And so I tried to summarize that. I gave an example. I talked about order of operations, or operator precedence, rather. And then now this might have been a little confusing. I talked about how you actually, the bit manipulation is one part, but you obviously have to get the data from the peripherals and to the peripherals. How do you do that? Well, in C, the way you do that is through this dereferencing operator, the star. But I also mentioned that I think on the Arduino, when I say Arduino, I mean the Atmel ATmega 328P, which is the quintessential Arduino chip. There's multiple Arduino processors, but the quintessential one, the original, the OG, was that 8-bit Atmel chip. When we programmed that, we used dereferencing, right? But when you program on more complex architectures like the ESP32 or even the Neos that we use in 313, generally you don't use just dereferencing. Generally in that case, you're going to use some kind of a macro or an intrinsic, and that's what we're going to use in this class. We're going to use reg read and reg write. So just keep in mind that under the hood, I think these are probably just dereferencing, maybe, or maybe these are using inline assembly language to generate specific instructions for, you know, I/O, accessing I/O device. I don't know.
They are just dereferencing.
Okay. So on the ESP32, these are just macros to the dereferencing operations I showed. But on the Neos processor in 313, those ones actually have to generate a load I/O or a store I/O instruction as opposed to a regular load or store instruction, which I think you get with dereferencing. Or maybe the compiler will do it right if you declare them as volatile. I don't know. But you should follow whatever the best practices are for the target chip. So I think on the ESP32, this is best practice, right? This is how people generally do it, right? Okay. So there's read reg and write reg. So this is how you read or write to a base, an I/O address. And then once you do that, then you have to worry about bit manipulation. And there's a little bit of a help there too, because we also have this reg set bit and reg clear bit, which is used to simplify that a bit. So if you want to set a bit, you just take a 1 and shift it to wherever you want to set. And if you want to clear a bit, you do the same thing, right? Now in this case, I'm clearing 3 bits, right? 1, 1, 1. And this would clear the bit field from bit 12 up to 12, 13, 14. So this would be 14 down to 12 clearing, right? Now the problem is that if you want to put a value in a field, then we don't have any help for that, right? If you have a 3-bit number you need to insert, then you're going to have to basically clear that field and then use a bitwise OR to put the value in, right, Alex? There's no help there, right? In other words, these primitives are single bit only, essentially. If you want to put a multi-bit value into a register, it's a little trickier, right? Okay, so okay, now this is something I don't actually completely understand this myself, but there are a few registers in ESP32 called D ports, and for some reason the compiler requires you to use these special macros when you access those, right, Alex? And I think there's only a few of these. So
yeah, these are really only for like turning on the box and pulling them out the peripherals off the preset. That's about it.
yeah, so but we'll give you additional guidance on that when we assign the labs. But just keep in mind that there's in a couple cases you have to use the special variant of the reg read, reg write, and set bit and clear bit. Okay, all right, and then I think I ended last time with this specific example. I don't want to go into too many details. We'll talk about this more when we assign the related lab. But the idea is one of the things you can use control registers for is configuring the pins. So these chips, all the kind of the Arduino family of microcontrollers, have pins that in some cases have specific purposes, like UART, for instance, console I/O, but then you can go and you can override them and you can use them for whatever you want them to use them for. And the way that works is through these muxes. You basically have a mux that you can set to change the functionality of almost any pin, not all of them. As I mentioned, there's 48 pins on this chip, and there's only 40 of them that you can mess with, right? And some of those 40 you don't want to mess with, because if you do that, you'll break the ability to write to the console, right? You'll break your ability to print messages, right? Or you'll break the flash RAM, right? Is there a flash RAM? Is there a couple pins for flash that you don't want to mess with?
Yeah, those aren't exposed on our board. They're only routed internally, but on other boards they are exposed.
Yeah.
So if you connect to those, it'll break SPI flash.
Yeah, so the point is that you have to be careful which pins you mess with, right? Also, the naming, it's a little weird, because you would expect, okay, there's 40 pins. They should just be labeled 0 to 39. Data 0 to data 39, all right? Good. No. They all have, you'll have pins that, like, for example, pin 12, you want it to be called data 12, but it's not. It has another name. It is pin 12, but it has some other name that's for what it's really supposed to be used for, but we're not going to use it for. So if you look at a pinout of, in fact, might as well bring one up here. Hold on a second. Let me show you what I mean by that. So if you say ESP32 pinout, you get a picture like this. Okay, And so this is the board that, well, this is not exactly the board we're using because they're all different, but this, oh, actually it is a VRoom 32. You see that each one of these pins has different names. So this is pin 12 that I was talking about, but it's also called SD Data 2 or HSPI MISO or Touch 5 or ADC 2.5 or RTC GPIO 15 or GPIO 12. These are all the different possible uses you can have for this pin, right? So this part gets a bit confusing, but again, we'll get into that more once we start assigning the projects for that. Okay, so get through that. And okay, now one other thing I want to mention. I've been complaining to you a lot about doing this bit twiddling and how it's prone to bugs and errors. There is a better way to do it that's offered by the C language. And this is pretty cool, but it's not really all that practical, but you may want to use it. So it turns out, and I only learned about this a few years ago, you can define a, in C, you can define a structure, right, which is basically the equivalent to a class, right, in C++. And in there, you can declare members of that class, right, just like you would normally. However, you can use this colon. Now, in C, the only time you typically use a colon in C is if you use the ternary operator, right? The trinary or ternary operator. But there's another usage of the colon in the C language, and it allows you to select a number of bits that member variable occupies within the structure. Okay, now you might say, wait a minute. If MCU select is 3 bits, then why did you declare it as a 32-bit? Well, that's kind of the weirdness of the syntax. You have to declare these as integers, right? Whose native width is at least the size of the width that you're giving, right? But ultimately, the number of bits allocated is determined by the number of bits. So in other words, what I'm trying to say is that I have something called MCU_IE. I declare it as a 32-bit unsigned integer, but I tell the C compiler that that's really only 1 bit inside the structure, right? And then when you put these in, you have to be careful that the ordering here is least significant to most significant. So if you look at a bit field in the ESP32 technical manual, you have to list these fields in reverse order, basically from right to left, right? So this is from right to left, right? So this is the least significant bit, and this is the most significant 17 bits, right? Which makes sense because the reserve bits are usually the most significant bits, right? So you have to put these in reverse order, okay? But then you also have to create a union, because a union is where you want to have a 32-bit value, which I call raw, is overlapping this structure, right? They're both occupying the same bits, right? But what this allows me to do is express these fields as a single 32-bit value, right, which is the control register, or I can go in and I can actually address specific fields in there by name, right? So I can declare something called struct io mux gpion reg, right? I can declare a variable like that, and then I can set a field by saying variable dot fields dot func WPU and just set it to something. So then I don't have to worry about shifting, masking, nothing. And it's completely, you won't have any bugs or errors doing it this way, because this is very clear. And the code will also become self-documenting as well, because when you read the code, the code will actually show you what field and what register you're setting. That's pretty cool. Of course, when you store it back to the hardware, you have to use the raw form, right? But that's okay. You just say .raw, right, as opposed to .fields, right? So this is really cool, and you might think, well, this is way better. This is way better than shifting and masking, because again, it's less prone to errors, and it makes your code self-documenting. You can see what's going on. However, the problem is that in order to do this, you would have to declare one of these structures for every single register that you want to use, and there are dozens or hundreds of them, right? So unfortunately, it's not really that now, if you're like my former student Charles, who loved to code in a beautiful way, right? He would probably do it this way. but there's going to be a lot of typing involved, basically. It's very labor intensive to do this in practice because there's just so many registers with so many different formats. And it would be awesome if Expressif would have defined these for us, and maybe they did and I'm just not aware of it, but as far as I know, they didn't. Okay, so you would have to do it. You'd have to do Expressif's job for them, which is meaning document their register space. Make sense? So here's an example where I use it. So I declare struct io mux gpion reg myreg, and then I say myreg raw is a reg read. So I read the register. Of course, I also have to have the address of that register, which in this case is gpio12 reg. I'm going to read that into the raw union, right, the raw part. And then by doing that, I will have populated all the fields because of the union. And then once I have those fields populated, I can then just select one field, SLP select, set that to 1. And then I can write that register back with the raw again, right? So this is a much more elegant way to do it than what I showed you guys before. And of course, what's really happening here is the compiler is just putting all those masking and shifting operations in for you. In other words, you're making the compiler do all the work of masking and shifting. But like I said, it's up to you if you want to do it this way or not. I thought I would just show you this as an alternative approach to this. Okay, so here's an example question. Write a line of C or C++ code that sets the value of bit 4 to the value of 0 in the variable named myvar, leaving the other bits unchanged. So in this case, I'm not doing, this is just assuming I've got myvar. This actually isn't doing the IO. So I'm going to take myvar and I'm going to AND it with the complement of 1 shifted 4 bits to the left. So again, now you could do this in multiple lines of code too, obviously. I've chosen to put everything on one line, which unfortunately, like I said, that increases the possibility of getting an error. But in one line of code, that'll set that bit to 0. Okay, so this question is kind of asinine. This is a question I came up with a few years ago to torture students. Considering the following snippet of C code, indicate which of the following lines of C code will cause the same value to be stored in variable y. So in other words, which one of these 4 values is equivalent, or which one of these 4 lines of code is equivalent to that one in terms of the functionality? Very difficult to figure this out, but basically what's happening here is that this line of code is taking x and it's taking the upper 4 bits of x and putting them in the lower 4 bits of y, and the lower 4 bits of x and the upper 4 bits of y, and then it's additionally negating or bitwise complementing the upper 4 bits, right? So I used to go through this step by step, but this, over the years of, this question is just, no one would ever do that. So it's just asinine. Okay, so I'm going to change topics here a little bit. We want to talk quickly about pulse width modulation. So have any of you guys heard of this, pulse width modulation? A few? Okay, so pulse width modulation is when you have a binary signal and you want to carry an analog signal on it, essentially. It's a poor man's analog. One way to do analog with a microcontroller is to use a digital to analog converter, but those are expensive. They take a lot of space on a chip, and sometimes they're overkill. So when you're now in cyber-physical systems, when you control a motor or when you control a power electronics, some kind of power converter, like a DC-DC converter or AC-DC converter, DC-AC converter, all those converters, all those power electronic circuits use pulse width modulation to control, right? And like I said, motors, and also you can use them for, you can even use them for sound, for audio, for sending audio. So in other words, the idea is that you have a digital pin and you want to use that digital pin to essentially connect to a speaker and play music, right? How do you do that? So this is one way to do it. LEDs too. All the LEDs use this, right? So whenever you have an LED that dims and brightens, that's being done through pulse width modulation as well. Yeah. So how does that work? So basically, the way it works is that the digital signal is switched on and off at a certain fixed frequency. So, but what I mean by that is that if you look at the signal and you look at the time from a rising edge to the next rising edge, or from a falling edge to the next falling edge, right? If you measure that period, it stays consistent, right? So PWM has a fixed frequency. Now that's not there's other modulation techniques that don't make that assumption, but in PWM there's a fixed period. The thing that changes is what they call the duty cycle. The duty cycle is what percentage of that period the signal is high as a fraction of, or as a portion of the total period, right? So if it's high for 50% of the time, which is what you have like in a clock signal for a CPU, generally in a clock signal, it's high for half the time and low for half the time. In a PWM, you want to adjust that duty cycle in order to carry an analog value. So for example, this would be a 0% duty cycle is where you actually would never be high, but any non-zero duty cycle, you would see this period, the periodicity of the signal. And then for 10% duty cycle would mean that it's high for 10% of the time and low for 90% of the time, right? And then likewise, if you have 100% duty cycle, it's just, basically just DC, right? Always high, right? So this way, I can carry an analog value. Now, you might say, well, it's not analog, it's a percentage. Well, right, but that percentage, when multiplied against the voltage of the PWM signal, is interpreted to be the analog equivalent, right? So if you have a 5-volt signal and there's a 10% duty cycle, then that would be a signal that would be 500 millivolts, right? 10% of 5 volts. Does it make sense? Okay. And so, yeah, that's basically all there is to it. It's pretty simple. But you might say, wait, well, how do we know about the period, though? Like, how do we set the frequency? How's the frequency determined? Well, that's tricky. There's actually some trade-offs there. When you turn up the frequency on a PWM signal, it burns more power because you got your transistors are switching faster, and every time you switch, you get dynamic power loss. So it's going to cost you to crank up the frequency. But on the other hand, depending on what application you have, you may benefit functionally from having a higher period, right? Depending on, so for example, in power electronics, if you want to shrink your converter, like back in the day, a power converter used to be big, right? Because they had to put big capacitors in there, right? But there's been this trade-off where they've been able to shrink power converters by having smaller capacitors, but then that requires that you have a higher switching. Your switching frequency has to be correspondingly higher. So there's various reasons, depending on what you're doing, of how you would want to set this frequency, right? Generally speaking, though, the frequency should be fast as compared to the dynamics of the signal that you're modulating, right? So if the signal that you're modulating, and now I'm not modulating this one actually, these are all DC values that I'm sending through, right? So what happens if I have an AC value, right? So here's a better example. So let's say I have a sine wave, right? So this is one period of a sine wave, and this is a 1 millisecond period. So this is a 1 kilohertz sine wave, right? 1 kilohertz signal. And so what I want to do is be able to send this sine wave along a PWM carrier, right? So the way you do that functionally is you first have to decide what the frequency is of the PWM signal. Now, if this is 1 kilohertz, if I want to send a 1 kilohertz signal, then my PWM frequency has to be faster than that. It has to be hopefully a lot faster, usually a lot faster. In this case, it's 1,000 times faster. So I have a PWM period of 1 microsecond, which is a megahertz, right? So I'm going to take this 1 kilohertz signal, AC signal, I'm going to modulate it on a 1 megahertz PWM. So the way you do that is you create a sawtooth signal. A sawtooth is where you have this value that basically for every period, for every 1 microsecond period, it goes from 0 to 1 and back to 0, right? So it linearly goes from 0 to 1, and then it drops to 0 for the next period, right? And then you take this sawtooth signal and you just have to compare it to the sine, right? And whenever the sawtooth signal is less than the value you want to modulate, then the PWM is 1. And whenever the sawtooth signal is greater than the value you're modulating, you set the PWM to 0, right? So what you end up seeing, and the way I plotted this one is I used an area plot where the area under the curve of the PWM signal is colored, right? So the reason why you're seeing this coloring is because whenever the PWM is high, it's blue, right? And whenever it's low, it's white. So you can see what's happening with the PWM is as the sine wave goes high, you see more blue because the duty cycle is higher, right? And then when I get down to the bottom here of the sine wave, there's more white. That's because the duty cycle is lower, right? So this is what a PWM version of that sine wave would be. So basically what you're doing is you have the sine wave, which is x of t. You're sending it into some kind of a modulator, and then you're getting another signal, x PWM of t, and then presumably you have some kind of demodulator somewhere, which is going to convert that back to x, but you're not going to get an exact x. You're going to get an x hat, which is you're going to have some distortions here because of the modulation. So what ends up happening to that x hat is you end up with some extra dynamics in that signal. You have some energy at all the harmonics of the original PWM frequency, right? Meaning high frequency. Meaning that if you plug that directly into a speaker, you'll hear what Alex heard, which it had this high frequency whine that hurt his ears, right? So in order to fix that, there is a way to fix that. You can apply a low pass filter on that output to try to filter out the high frequency garbage that you get on X hat, right? And that's exactly how they do the greeting cards that sing in the store. And even now you might say, well, yeah, because they're cheap, right? No, you can buy a very expensive Class D audio amplifier, which are used they're not usually used in high-end audio applications, but if you have any kind of a public address system where you need a lot of power, a lot of volume, but you want to try to make it efficient, those ones also use the same technique. This is PWM with a low-pass filter. That's called a Class D amplifier, right? Okay, any questions about that? Okay, so you might say, now, why is this relevant to this class? Well, because like as I mentioned, in cyber physical systems, you have a computer that's manipulating the physical world, right, in some way. And generally, one of the ways you do that is through motors or servos or stepper motors, and those are all controlled by PWM, right? Additionally, we're also going to use a PWM. No, it's not the same thing. We're using a similar type of system as for an input, but that's different. So we're going to be using a PWM signal to control some stuff, hopefully. Like I said, if everything works out well, we'll have some kind of a self-balancing cube, and we're going to use PWM to control the motors that balance the cube. Okay, so here's an example question. What analog voltage is generated with a 3.3 volt PWM signal having a 30% duty cycle? You just take 3.3 volts, multiply it by 0.3, and that's 0.99 volts. Okay, all right, so now I'm going to switch topics again and talk about interrupts. So when I talked about programmed I/O, I mentioned that that's all initiated by the CPU. The CPU can read or write values in a peripheral, but if the peripheral wants to be proactive, it can't. It's powerless. Unless the CPU performs a programmed I/O, the peripheral can't do much, can't get the CPU's attention, unless you use something called interrupts. Interrupts are a way for the peripheral to signal to the CPU that it needs attention, but the expectation is that after it does that, the CPU will then do programmed I/O to address it, right? So the peripheral can't just send data to the CPU, but it can issue an interrupt, get the CPU's attention, and then have the CPU do the programmed I/O to figure out what's going on and to address the situation, right? So interrupts are used in, that's what happens when you hit a key on your keyboard, or when a packet is received from the network, or when the disk drive is finished fetching data from the disk, or when there's a page fault or any kind of unexpected error happens inside a computer system, you get an interrupt or an exception, which are a similar idea, or a trap. They used to call them traps back in the 80s. So you've got these, essentially an interrupt is just a bit, one wire, sends a signal to the CPU. So the way this works is that the CPU is sitting there just doing its thing, executing code, and you have this interrupt wire that's going from the peripheral to the CPU, and it's a bit, so really all it can do is toggle, right? So you toggle it, go from 0 to 1, and the expectation is that the CPU will see that and will automatically, through a hardware mechanism, this is implemented in hardware. So you guys might think, wait a minute, we didn't have interrupts in 611. Yeah, because we didn't add, our 611 CPU did not have interrupt handling support. We used to back in the old days, but we dropped that. So you got a signal comes in, and then the CPU behaves as though it had executed a jump instruction and goes to something called an interrupt service routine, right? That's been registered, it's been baked into the hardware somehow, right? And then it executes that ISR, and then it, and typically this ISR usually is a bunch of programmed I/O stuff, right? Reading and writing I/O addresses. And then when it's done, it resumes what it was doing before the interrupt occurred, all right? Now the problem is, and this is something that came up with when we used to use the Atmel chip. So the Atmel chip had a very simple interrupt mechanism. It was just wire, it did this, right? That was it. The problem is that, now the Atmel chip, by the way, could use level triggered or edge triggered, right? So you could set it up, and I'm sure the ESP32 is the same way. You can have this triggered by this being high or by the rising edge, right? But in either way, you've got some issues with that. So problem is that there's no synchronization. Oh, I screwed up the animation there. The problem is there's no synchronization here beyond the interrupt and the CPU responding to it. So for example, the peripheral has no idea how long to hold the interrupt high, right? If it's assuming it's level sensitive, right? So if the peripheral holds up the interrupt for a really long time, and the CPU gets done with the interrupt service routine and goes back to what it was doing, and then it's going to see that interrupt is still high, it's going to accidentally perform 2 interrupt service routines, right? Because, there's no way for the peripheral to know how long it takes the CPU to service the interrupt, right? So you just kind of have to guess how long to hold that interrupt high. And on the other hand, you can have the reverse problem where the peripheral may want 2 interrupts, may issue 2 interrupts within the time it takes to issue 1 interrupt service routine. So you can either accidentally double trigger an ISR, or you can miss an ISR if the interrupts are being issued faster than the CPU can keep pace with, right? So that's a problem. And then also, if you pulse the interrupt really fast, the CPU may not even notice it, right? It may miss it entirely, right? So I have no idea how long to hold that interrupt pin high. And there was really, as far as I could tell, no solution to that with the Atmel chip. Now, the way that more sophisticated processors like the Neos work from 313 is they use an acknowledgement. They have an acknowledgement mechanism where you have an interrupt pin going from the peripheral to the CPU, but then the CPU has a return wire called the acknowledgement that goes from the CPU back to the interrupt. And this is really nice because now you can do this handshake where the peripheral only needs to drive the interrupt pin high, right, and keep it high until the acknowledgement goes high, right, from the CPU, at which point the peripheral knows that the CPU has acknowledged the interrupt and is executing the interrupt service routine, at which point the peripheral can then drop its interrupt right? And then it knows that it can't issue another interrupt until the acknowledgement for the CPU goes low, which indicates that the CPU has finished processing the interrupt, right? So it's a 4-step handshake that has to happen, right? I request the interrupt, he acknowledges, I drop my request, he says he's done, right? And I don't even know how the ESP32 handles this, if it has an acknowledgement or not, but that's the way, I know that that's how the FPGA-based soft-core processors have. All right, so suppose you have a peripheral that's connected to the CPU's external interrupt input. Assume the peripheral can change the value of the external interrupt no more frequently than once every 50 microseconds. And by the way, the reason I bring this up is because we're dealing with real-time systems here. Cyber-physical systems have to interact with the environment. So like if you got the cruise control on your car going, the cruise control computer has to tell the engine to change to accelerate or decelerate. And if the cruise control system needs to be synchronized with the response time of the engine, right? Obviously, you don't want to say go faster. He's not going faster. Go faster. He's not going faster. Go go go. You know, and then you end up spooling up just because of the difference in timing, the response rate between the CPU and the engine. And so it's important to be aware of this stuff when you design a cyber-physical system. So in this case, I'm saying assume that you can change the value of the interrupt no more than every 50 microseconds, and the CPU can execute an interrupt in 75 microseconds. So what's the maximum number of interrupts per second possible when using edge-triggered versus level-sensitive? Well, it turns out it's the same number because the bottleneck here is this sentence here. You can change the interrupt no more than 50 microseconds, which means 50 microseconds high, 50 microseconds low, right? So if you're going high, low, high, low, high, low, it's going to be 100 microseconds, and that would be for edge triggered or level triggered, unless you can just hold it high. Another option is you can just hold it high, and then in that case, you might be able to have it, respond every reciprocal of 75 microseconds. But I didn't specify whether this has an acknowledgement or not. Okay, any questions? All right. Okay, so change topics again. Interface protocols. So this is involving how chips talk to one another. So I mentioned that we're using system on chips, so you've got different peripherals and different processor cores on one chip. So there's a protocol that IP modules use to communicate on chip, and then there's ones that they use to go off chip, to go from chip to chip, and then of course there's board to board, right? So there's different protocols, generally depending on how much of a distance you're going. So for on-chip interconnects, like if you have the CPU talking to the SPI peripheral, those generally are going to use a parallel bus, right? Whereas if you go off-chip, generally you're using a serial bus, one wire. They still use parallel buses for off-chip. I think the last thing they use those for now is for memory on a computer. In a typical PC, you have a CPU, and you got RAM, and they use a parallel bus where they send whole words, 64 words in parallel. But in every other instance, like when you have SATA or PCI Express or DVI or HDMI or DisplayPort, all those are serial buses. Generally, when you go farther distance, you use a serial, 1 bit at a time. And then there's also different, you have to choose your interconnect technology and your protocol based on what kind of speed you're expecting it to do as well, right? So there's high performance ones and low performance ones. So there's a whole bunch. In this class, we're going to focus on the slower ones that are used for embedded systems like the ones we're using. And so those ones they can either be asynchronous or synchronous, meaning that whenever you have two components communicating, they have to synchronize somehow. And that can be done in a synchronous bus. It's done by sending a clock signal, right? So you have a clock signal that's part of the bus, part of the channel, right? So I mentioned it's bit serial, so you may only send 1 bit at a time, you may only receive 1 bit at a time, but included in that channel, in addition to the data bit, you have a clock as well, and that's the synchronous, right? And then there's asynchronous, which is where you don't provide a clock. Now, how do you synchronize if you don't have a clock? Well, there's basically 2 ways. One is you can basically have both parties agree on a clock rate, and then they can both use their own internal clocks. That's the way UART works. That's the way console I/O, like when you plug in and you just want to print text, right? In that case, you just agree on what they call a baud rate, right? And then you generate an internal clock on both ends at that speed, and then you just use that clock, right? But that only works at very low speeds. And the reason is because this concept called metastability. When the data comes in, you have to make sure that data coming in is stable for an amount of time before and after the clock edge, right? It's called, we talked about that in 611, actually, towards the end. Most people had kind of checked out by that point, but one of the last lectures I gave in 611, we talk about timing closure and timing analysis. And on chips, it's very important that when you sample data using a flip-flop or a register, you cannot change that data around where that clock edge happens, right? Well, if you use an asynchronous bus, there is no guarantee of that at all. You know, so like if you use UART, I may send you a bit which just happens to change right around the time your internal clock is transitioning, right? At which point you get an error, and there's nothing you can do about it, which is why UART has error detection capability built into it, because you get a lot of errors with UART, but the probability of getting that error depends on the frequency of the clock. So if you have if you try to run UART at a megahertz, 1,000,000 bits per second, you're going to get a lot of errors. If you run it at 57 kilobits per second, you're not going to get a lot of errors because there's a lot of dead time between clock edges, right? When you have a slower clock, right? Does it make sense? So you can do an asynchronous bus very slowly. Now, what happens if you want a fast asynchronous bus? Well, then the way you do that is you take the data bits that are being sent, and you encode them. Use something called 10-bit, 8-bit encoding, which is for every 8 bits you want to put in the bus, you package it as a 10-bit value. And the purpose of that encoding is to maximize the number of transitions in that data stream. So for example, if I want to send all zeros, I'm like, all right, I'm sending you all zeros, 0, 0, 0, 0, 0, 0, 0, 0. You're not going to see any transitions in there. But if you encode it with an encoding scheme, the 0 word actually is not 0. It's a collection of ones and zeros. So what ends up happening is that you can use a phase lock loop at the receiving end to extract the clock signal from the data. And so that's how HDMI works, that's how SATA works, that's how all of these high-speed serial connections work that are asynchronous. You can't send a clock, you just send the data, an encoded version of the data, which then you can use an analog circuit to extract the clock out of it. Make sense? But we're not going to, that's way more advanced than anything we're doing, right, in this class. Okay, so does it make sense? So that's synchronous versus asynchronous. Asynchronous, no clock. Synchronous has a clock. Okay, so the first protocol I want to talk about is SPI, just because this is a very common one in embedded systems. It stands for Serial Peripheral Interface. And the nice thing about SPI is if you understand how SPI works, it's very easy to understand other protocols. It's very indicative of how other protocols work, right? And so SPI is synchronous, so there's a clock. So you send one bit at a time, but you also send a clock signal. It's also a master-slave, meaning that whenever you have a channel, meaning there's two peers that are communicating, one of them has to serve in the master role and one of them serves in the slave role, meaning that only one of them can initiate communications, right? And the other one has to basically respond to those communications. Make sense? So it's not like Ethernet. It's not a multi-master. You can't change who the master is. The master and slave rules have to be fixed and they're not changeable. Okay? And it's the master side that drives the clock, which is actually nice because if you have an asynchronous bus like you are, both sides have to agree on what the bus speed is, right? What does that mean? That means every time I've ever plugged a console in, I always have to guess, trial and error what the stupid speed is, right? Like I plug into an FPGA, I have no idea what the speed is. So you got to try them all until one works, right? But with SPI, you don't have to do that because if I plug a slave into a master, that slave knows exactly what the speed is because it's receiving the clock signal over the channel, right? Okay, so I mentioned that. Okay, so the channel is comprised of 4 separate signals. There's something called S clock. Now, oh, by the way, these names are not fixed. Sometimes these names are slightly altered, but their functionality is not. Depending on what you're looking at, you may see different names here. These are not standardized names, but in an SPI channel, there's always 4 signals. There's always going to be a clock. There's going to be what's usually called MOSI, which is the data pin. But it's the data pin going from the master to the slave. And then you've got another one called MISO, which is master. So MOSI is master out, slave in. MISO is master in, slave out. MISO is the data pin coming back the other direction. So this is a bidirectional protocol. You can send and receive a bit at the same time, right? Which is pretty nice. And then there's a slave select pin, which is the way which indicates whether the channel is is in the process is active or not, whether it's in the process of communicating. Make sense? All right, so now in order to save power, because setting a clock is expensive power-wise, you don't want to always have the master continuously clocking the channel. So the clock is actually dead whenever the channel is not being used. And so the clock is idle, right? It's just a flat line unless something's going on, and then you kick the clock in. So that's efficient. And then there's an active low, this slave select, sometimes called chip select. This signal is what indicates whether the channel is alive, whether it's active. And it's active low. Now why? Don't know why. That's just there to confuse people, right? Meaning that when the channel's not active, it's 1, and when the channel's active, it's 0, right? Okay. All right. So so conceptually, what's going on with SPI is that it is a byte-oriented protocol, meaning that it's byte-oriented, but it's serial, which means that what's happening is it takes 8 cycles of the clock, the channel clock, to send 1 byte from master to slave. However, there's also that meso wire, so the slave is simultaneously sending data back to the master. So what's happening here is that you're really doing an exchange. You've got 2 8-bit words that are being swapped. Whenever the channel is active, you're swapping 2 words. Master sends 1, slave sends 1, right? And the way they usually show it is kind of through this is showing it like a shift register, right? Where you're shifting bits out of the master into the slave and from the slave back in the master, and you're doing kind of like a little you know, just swapping them, right? Okay. Okay. So but to add a little bit more complication to this, there are 4 different modes the channel can be in. And this is something, unfortunately, like the UART, you know, like with an asynchronous where you have to pre-agree on a speed. You don't have to pre-agree on a speed because you got the clock in there, but you do have to pre-agree on a channel mode, right? And so there are 4 channel modes, and that is determined by the clock polarity, C pole, and CFA, which is the clock phase. You guys with me? So these are 2 bits, and 2 bits you can encode 4 values, right? 2 to the 2nd power. So the clock polarity is pretty simple. It just determines when the channel's not active, when the channel's idle, should the clock be high or low, right? If CFA is 0, the clock is low normally, and if CFA is 1, the clock is high normally, right? And then the clock phase, now this is the one this one's kind of confusing. The clock phase determines which edge of the clock should the first read be performed on, right? So if you remember from 611 when we talked about time enclosure, if you were there, if you saw that lecture, an edge-triggered flip-flop uses the edge of the clock to sample the input data, right, and then capture it inside of it, right? So the way I always think about it is like during that rising edge of the clock, if it's a rising edge flip-flop, you kind of take a snapshot of the data and you store it internally, right? Now, we also, you know, in 611, we talked about how there's an aperture time, meaning that the input has to be stable for the setup time before that edge and for the hold time after that edge, right? And the setup time plus the hold time is called the aperture time, which is, I think, a great analogy because it's like a camera. It's like the shutter speed of a camera, right? If you take a picture with a camera and you have to set the shutter speed to freeze, you know, motion, right? So and if there's any movement of what you're taking a picture of within the shutter time, right, then it'll be blurred, right? You'll get motion blur, right? So it's the same kind of idea with this. Now the flip-flops though can be rising or falling edge, right? So the problem is that when you have an SPI channel, you have to basically figure out what edge of the clock you want to read the data on, which is really important because the whole point of SPI is to avoid metastability. You want to make sure that the data does not change within the aperture time of the clock, right? So the whole point of this is to ensure that you are changing your data on one edge of the clock and then you're sampling it on the other edge of the clock. That way, hopefully, the input data on the SPI channel is stable for half a clock cycle before the edge and a half a clock cycle after the edge, right? You want to guarantee that, right? Okay, so what that means is that, for example, if C pole is 0, meaning that clock is going to be 0 when the channel is not active. So in this case, you can see it starts out as 0, right? And then if CFA is 0, that means I'm telling the receiving end, and remember the slave and the master both receive, depending on which bit, right? The slave is receiving MOSI, the master is receiving MISO, right? So both the master and slave side have to decide what edge of the clock they want to capture the data on. So if C pole is 0, meaning the clock starts out as 0, and CFA is 0, which means use the first rising edge, then what's the first rising edge? Sorry, I gave it away. What's the first edge is rising, right? Because the clock is normally low. I want you to sample on the first edge. If the clock is low, the first edge must be rising, right? Because you're starting from low. So you'll notice that MISO and MOSI are both transitioning one cycle before that rising edge, right? So in other words, what this means is that when CFA is 0, it means that MOSI and MISO get a head start. They change one cycle ahead of the first transition of the clock, right? Which means that if you look at when these guys change versus the clock, you're moving it to the left, right? That way, on the first edge of the clock, these guys are stable and you're not going to get metastability. You're not going to risk metastability, meaning an error, right? And this is why SPI has no error correction mechanism. It doesn't need one because it's really robust because we're very careful about the timing of the clock versus when the data changes, right? So the data changes 1/2 clock cycle before that edge, right? Okay, does that make sense? Okay, so then I mentioned that it's byte oriented, which means that you can expect there to be 8 rising edges because it's a bit serial protocol, 1 bit at a time, but it's byte oriented, so we're going to exchange a byte, 8 bits. So how many rising edges? We should have 8. 1, 2, 3, 4, 5, 6, 7. I get that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, right? There's 8 rising edges, which corresponds to the 8 bits that are being exchanged, right? And each rising edge is clear of transitions in the data, right? So in this case, these dotted lines indicate the data changing, right? But in between the dotted right is where you sample. That's the sampling clock edge, the rising edge, right? Okay, now, so that was what I showed you here. Now let's look at an example where C pool is 1 and CFA is still 0. In this case, it's the same idea except the clock starts out high. So everything is the same except I sample on the falling edge of the clock, right? And so notice again, C pool is 1 and first falling edge I sample on, right? Also notice that the data is changing again 1/2 cycle before the first falling edge, right? So I get a nice aperture time there. Okay, now what if CFA is 1? Okay, well notice here, MISO and MOSI happen to be changing with the clock on that rising edge, right? That's probably not good. All right, that's not good, right? However, because CFA is 1, it means that I'm sampling on the second edge of the clock, right? So what's happening is if I look at falling edges here now, why is it falling? Well, it's falling because clocks start out as 0, but CFA is 1, meaning that I ignore the first rising edge, I sample on the falling edge. So we have 1, 2, 3, 4, 5, 6, 7, 8 falling edges. I sample the data on the falling edge, which is the second edge, right? So CFA means second edge, start on the second edge of the clock, right? And then if C pool is 1 and CFA is 1, the clock starts out as 1, but I still sample on the second edge, which happens in this case to be the rising edge because of C pool, right? So now the problem with this is that if you get this wrong, if there's a disagreement between the master and slave on these settings, it's devastating because basically it guarantees that you have the worst possible signal integrity situation you could possibly have, which is where you're deliberately, if you get this wrong, the master is going to deliberately change the data on the same edge of the clock that the slave is sampling it, which is the worst. Like you're asking for it to be screwed up, right? If you get it wrong. So it's really important that you get these set up correctly, right? When you set up the system. Any questions about that? Okay, so what is the issue? There is an issue though. The issue is that there is no, I have never seen an application that requires an exchange of 2 bytes, a simultaneous exchange of 2 bytes. In other words, this protocol actually doesn't make any sense at all, in the sense that if I have a CPU connected to an accelerometer, a sensor, any sensor, CPU sensor, CPU actuator, you never have a case where you need to simultaneously exchange 2 bytes of data between the CPU and the peripheral. It never happens and it's never needed. It's completely useless to do this. I mean, I've never seen an application where you actually demands this simultaneous, right? So what ends up happening in practice is that in every peripheral I have ever seen, what ends up happening is that you don't take advantage of this bidirectionality of the channel. You basically have one side dead while the other side sends something, right? You use it in a unidirectional way, and you just have to waste the pins to make it bidirectional, right? You guys with me? Okay, so here's a question I might give you. In the following SPI exchange, what is the value sent from the slave to the master? So how do we solve this? Well, first you have to figure out when to look at the data. And these dotted lines are here to help you, but you have to figure out what the dotted lines are indicating. The dotted lines in this case are indicating when the data should be sampled, because this is CFA. CFA is 1 rather. So it's the second rising edge. The second edge is where you sample. So there's the second edge of the clock, which is the rising edge, right? And so what I can do is just look at these rising edges starting from the second, right? And then just map that down to what the data is. And luckily, the dotted lines just happen to intersect those rising edges. So all I got to do is figure out what MISO and MOSI are when the dotted line intersects them, right? That's all you got to do, right? So, and by the way, the question is from the slave to the master, so I'm looking at master in, slave out, MISO. I'm ignoring MOSI right now. And then I'm just gonna look down here and I'm gonna pretend like I'm the master reading the value back from the slave, and I'm gonna look at that second edge, which is the first rising edge, and it's just 1 0 1 1 0 1 0 1, right? Now it's also shown that this is most significant bit first, so these are going to be, when I record these bits, I can just leave them in the original order, left to right, right? Now if it's least significant bit first, then obviously you're going to have to reverse the order of the bits. Okay. I think SPI, if I remember correctly, SPI could be either one, depending on the application. So you have to be aware of that. Okay, any questions? All right. What's the value sent from the master to the slave? Same idea, basically, except it's master to slave, so you use MOSI, and then you just have to figure out where you're going to read the data. So in this case, I'm reading the data in between my dotted lines, which I just superimpose over the existing dotted lines there. Okay. All right. So I mentioned that. See how much we got. We still got time. 10 5. Okay, 8 minutes. Okay. So I mentioned that doing an exchange of 8 bits between a CPU and a peripheral is basically useless in practice. No one ever does that. The way it actually, what you want is you want a transactional protocol, much like programmed I/O. You know, in programmed I/O, I said, you know, you can read an I/O address to get a status register, and you can write an I/O address to get a control register, right? I want to do this over SPI. So first of all, I need a concept of an address because there's no address in SPI. There's not even an address specified in the protocol. It doesn't exist. It's just an exchange of 2 bytes, right? So I need a way to put an address in the protocol somehow, right? Also, the problem is that I can't expect the slave to send me data for an address that it doesn't even have yet. In other words, there's no way that I can simultaneously send the address and get the data back if I'm doing a read, for instance. Like I can't say, read address 12, but make sure you're sending me the contents of address 12 as I'm sending you the actual address of 12, right? It's impossible. The slave can't know what address you're sending it until you've sent it the address, at which point it can then subsequently send the data back that's at that address, right? Likewise, if I want to write, I have to send the address first and the data I want to write second, right? So what that means is that in order to do a programmed I/O style transaction on top of SPI, I have to process it as multiple exchanges. You guys with me? So I have to perform multiple 8-bit exchanges in sequence. The first exchange, I send the address, and then the second exchange will be the data, the payload, right? So I have to do like 2 exchanges. Make sense? I also have to tell it if it's a read or write, which is part of the first exchange. So you could think of this as a header. Like in networking, you have a packet and there's a header in the packet and then there's a payload. SPI is the same idea. You send the header first in one exchange, and then the second and third and sometimes more exchanges, you send the payload. Guys with me? But what that means is that if you do that, you're guaranteed to only be using half the wires. You're still never going to use MISO and MOSI at the same time. Never. One of them is always going to be dead, right? So even though you have a bidirectional bus, you will never use it as a bidirectional bus. You're always going to use it as a unidirectional bus, where only one side is talking at a time, right? Kind of dumb, right? I don't know why people use this. It's absurd. It's really bad. It's really, really bad. So for example, it'll look like this, right? In this case, I'm doing 2 8-bit exchanges. The first exchange is the packet, is the header. The first bit is whether I want to read or write. The second bit is if I want to do multiple or single. And then I have 6 bits left over for the address. And then in the second exchange, I transfer the corresponding data, which will either be from the master slave or the slave to the master. Either way, you're only using half your channel, right? Okay, so that was for this figure is actually wrong because I got this from a book, I think. But so when you do a read, I send the address and then I get the data back from the slave, which means that the SDI, the master is not going to send anything during that second exchange. So this should be flat here, right? On a write, I don't need the MISO at all, because in the first exchange I send the header, which is the address and the intent for the write, and then in the second exchange I send the data I want to write, right? So nothing comes back from the slave in that case. It's just a flat line. Okay, so here's an example for that. So in the following SPI transaction, oh no, notice the terminology here too. In exchanges where you exchange 2 bytes, right? That's kind of like, you can think of that as a primitive operation, right, on the SPI bus. Whereas a transaction is a higher level protocol that uses multiple exchanges to perform a read or write operation to an address, right? So this is a transaction, meaning that I need two exchanges, right? And so in the first exchange, the least significant 5 bits, the address is in the least significant 5 bits, and the read-write flag is in the most significant bit. That's the header, basically. That's the header format, right? So what's the transaction? Well, if I look at the waveform, I don't even know if this is, like, right off the bat, I don't know if this is a read or write, right? However, if you look a little bit more closely, you can see that MISO is dead the whole time, right? So based on that, I can tell, even without looking at the bits, I can tell this is probably a write, right? The master's sending the address and the data because it's writing. The slave has nothing to do with it. So this guy is dead. So this is probably a write, but I can confirm that by looking at the bits in the header. So first of all, I have to figure out where to read the data. So pretty much it's, really one way to look at this, instead of looking at CPOL and CFA, all you really have to do is figure out which edge of the clock is the data stable for, right? That's really all you got to do, right? So obviously, CPOL is 1 because the clock starts out high. CFA is 1 because the clock and MESO start changing at the same time. That's a giveaway that the phase of CFA is 1, right? So I just have to figure out, like, well, okay, if these guys are changing at the same time, I got to go 1/2 cycle ahead, right? So I'm going to look at rising edges here to figure out where to read the data. So I'm going to position my dotted lines around each rising edge. That makes sense? That way I can look between falling edges to figure out what the data is. So I'm just going to decode this. So MOSI is 11001000, and you have to basically just count 8, right? You count 8 of those, you get the first word, the first byte, and in that first byte, the most significant bit, which is this guy, pretty much the first bit sent, indicates read or write. And notice I have a bar over read and nothing over write, which means 0 is read and 1 is write, right? So that first bit is 1. That means I'm doing a write, which confirms my earlier suspicions because it was obviously a write because it was just the master talking, right? So that's a write. And then I want to look at the least significant 5 bits to get the address. So that's bit 7, bit 6, bit 5, and then I want to look at bit 4 down to 0. So 4, 3, 2, 1, 0. And so that number is, what is that? 8, right? 8 in binary, assuming most significant to least significant, right? It says that there, yeah, most significant bit first. So that's 8. So that's it. So I'm writing to address 8, right? Then what do you want to write to address 8? Well, that's pretty much just the second word, which is going to be 1011, which is 8 plus 3, 11B, right? B and 5, B5. So it says write B5 in hex to address 8. Right? Now the problem with SPI is that this format of the header is not standardized. There's no standard for this. So depending on the peripheral, the way that you interpret the header byte is different for every peripheral, right? It's not fixed like it is in other protocols, like I2C, for instance. This is all set up for everybody. It's consistent. But for SPI, it's like, kind of the Wild West, and everyone does whatever they want to do, right, with SPI. Okay, so in this case, I'm telling you that the least significant 5 bits of the header is the address, but that may not always be the case. You may have it in the most significant 5 bits, or it may be a 6-bit address or a 7-bit address, right? Also, I'm telling you that read is 0 and write is 1. That's also arbitrary. It can be whatever. So in order to understand what's going on, you have to have someone describe what the header format is, right? What the transaction format is. Okay? All right, I think I'm out of time. So we'll continue this next week, and like I said, we'll get the first lab. The first lab will be just to give you a heads up, the first lab will be software only, where you'll be reading these transactions out of a trace file and decoding them, right? So pretty easy.